Hello everyone, welcome to chapter 4, which is titled Atoms and Elements. And before I start the chapter, I wanted to introduce my two dogs to you, and the reason why I'm putting a picture of both of them there is because you may hear them, particularly this one, Foxy, during my lectures, because Foxy, the dog that you see close up in this picture, is recovering from surgery. As you can see here, she had a lipoma removed, and she also had a tooth removed. I think the tooth removal is bothering her more than this large incision. She's on lots of pain medication as well as antibiotics, but we still sort of had a bit of a rocky night last night. Lots of whining, lots of needing to be petted. So she is at my feet right now, thankfully resting comfortably, but you may hear her whine occasionally during the video, during my lecture, and I may have to stop to pet her, to comfort her. So sending her well wishes. Our other dog, Wally, is fine and happy in the background here. So this may be a little bit of an interesting lecture, but I wanted to introduce you to both of my dogs in case you hear them in this video or in subsequent videos. So back to atoms and elements. And when we talked about atoms in chapter 1, we said that elements are made of atoms. To try and comprehend the size of an atom, it's kind of hard to think about the size of an individual atom because they are so small. But most people know what a centimeter looks like. If we were to put the size of an atom in terms of centimeters, the diameter of a typical atom, and it's going to vary from element to element, but a typical atom is on the order of 10 to the negative 8 centimeters. So pretty darn tiny. The unit that scientists like to use when talking about sizes of atoms and molecules is this new unit called the Angstrom, which, yes, you do need to be familiar with. There's that star. So Angstrom, the symbol for Angstrom is an A with a funny little hat. It's a German symbol. 1 Angstrom is equal to 1 times 10 to the negative 10 meters. So pretty darn small. So not so much in this chapter, but in subsequent chapters, we'll be using the term angstrom when talking about sizes of atoms. So you should add this conversion unit to your repertoire of conversion units of being able to convert one unit to another when given angstroms and meters. So size of an atom, pretty darn tall, pretty darn small on the order of 10 to the negative 10 meters. When we first introduced atoms in chapter 1, we said that atoms make up elements, those things on the periodic table that we will visit more fully later in this chapter. And we said atoms of an element are identical to each other, but different than atoms for other elements. We also said that most elements exist as individual atoms. So for example, if I had a sample of Fe, which is iron, which is a kind of metal, we would see that metal consists of small atoms that are iron. So most elements exist as individual atoms. We can classify elements based upon where they are in the periodic table and some of their properties. I have those listed here. We will visit those more fully later in the chapter. But the take-home point is that most elements exist as individual atoms. That was from chapter 1. And hopefully you also remember that there are some elements that like to buck the trend. They don't exist in their most stable form as individual atoms. They exist as diatomic molecules. Dia meaning two, and a molecule is what forms when two or more atoms come together. So there are some elements that like to be diatomic molecules. And in chapter 1, I said that I would talk about which elements like to be diatomic more fully. And so here we are. So these are the elements that like to exist as diatomic molecules: hydrogen, nitrogen, fluorine, oxygen, iodide, chlorine, and bromine. And the way that I like to remember that these guys are diatomic is this mnemonic that actually I learned from Dr. Zappala, which is have no fear of ice cold beer. It's appropriate today. It's supposed to be 90 degrees today. But this mnemonic of have no fear of ice cold beer hopefully will help you remember which elements are diatomic. So for example, have, the H, that stands for hydrogen. The N in no stands for nitrogen. So using this mnemonic to remember which elements like to exist as diatomic molecules is useful. You just have to remember that for cold, it's not C for carbon, but Cl for chlorine. And with the beer, it's not B or boron, it's Br or bromine. So, however you can best remember that these are the elements that like to exist as diatomic molecules, you need to know that. Now, why these particular elements like to exist as diatomic molecules, we'll talk about much later on in the course. But for right now, just know that those elements, they don't exist as individual atoms in their most stable state. They exist as diatomic molecules. So when we talk about the theory that surrounds what an atom is, one of the first theories that is important to chemists is one from John Dalton, early 1800s, very important scientist and very religious man too. He was a Quaker. He was probably interested in science, I'm guessing, because he was colorblind. And so he did lots of experiments in his lab that was actually next to the parsonage with regards to biology and with regards to chemistry. And so it's his theory of what an atom is that sort of gets scientists started in talking about what exactly an atom is. So these are the tenets of his atomic theory. One of them we've already talked about in detail a little bit, which is that atoms combined in whole number ratio can describe compounds. And we also said that atoms of the same elements are the same. You don't need to, so I have his postulates of his atomic theory written in terms of bullets. I think the most important part of this slide is that you recognize that John Dalton's picture or model of an atom is something that's similar to a billiard ball model. When you think about a billiard ball, you think about something that's spherical and hard in shape, right? There's not much definition to it. You can't really see what makes up the billiard ball. So that's how John Dalton in the early 1800s visualized what an atom was, something that is spherical, hard, and uniform throughout. So we will talk about other scientists in the next video that try to define or refine his model of the billiard ball model.